Okay, so we're going to start off today with the law of sines and cosines. So we're going to dig back into our normal trig, SOHCAHTOA, etc. And we're going to be using those types of trig functions with non-right triangles. And so first we're going to prove how these work, and then we'll do a couple example problems, and then we'll be done. So we know that right triangle trig can only be used for right triangles, but most of the time in real life we have a non-right triangle. So how do we deal with that? So we're going to use the law of sines and cosines. So the first thing we're going to do on this triangle to the right is we are going to sketch an altitude from B, and we're going to label it K. So it's going to go straight down. So an altitude goes from a vertex down to the opposite side and forms a right angle. And so we're going to label this side K. So now I have two triangles. Do you see them? So I have this one here, and then I also have this one here. So I have two right triangles, and I'm going to write two equations. So I'm first going to use sine of A. So here's A right here. We're going to write an equation using SOHCAHTOA, so to kind of remind us what that means. So if I'm at A, sine would be opposite over hypotenuse. Hypotenuse is across from that 90-degree angle. So this one would be K over C. Then I have the sine of C, so I'm over here on this other side. And so good thing I don't need this piece down here, because opposite would be K, and then A is across from that 90-degree angle there. So this one would be K over A. So we notice that both equations have a K in them. So let's see if we can get K isolated for each piece. So I would have C times sine of A equals K, because I'd multiply both sides by C. And over here, I'm going to multiply both sides by A. And so I can see now that I have a K isolated in both of them. So if both of these things equal K, then that means both of these things have to be equal to each other. So I have C times sine A equals A times sine C. So if I wanted to move this around so that A is with sine A and C is with sine C, how would I do that? Well, I would divide both sides by A and C. So I would divide this side by A and C and this side by A and C. And so what I would be left with is sine of A over A is equal to the sine of C over C. And again, we're using lowercase letters for the side lengths and uppercase letters for the angles. Okay, so now that we have that, we know that this is part of our law of sines, and we're going to develop the other part in a second. But I also want to point out that it can also be rewritten as A over sine of A is equal to C over sine of C. So they're both equivalent depending on how you want to write it, just because they are ratios. So we can write it with the numerators, the denominators, doesn't matter. Okay, so we're going to do the same thing over here. We're now going to sketch an altitude from vertex C, and then we'll label it K as well. And so again, I have two triangles here. I have the pink one, and then I also have my blue one. All right, so I want to write what the sine of A is. So here's A, right angle. This means that this is going to be our hypotenuse. So this one would be K over B. Sine of B, so we're over here, would be K over A. So if I isolate K in both of these like we did before, and then if I regroup and make A with sine A and B with sine B, I would have sine of A over A is equal to sine of B over B. Or you could have it as A over sine A equals B over sine B. Both of them are equivalent. Okay, so if I wanted to take this pattern and extend it to B and C, so we've done A and C and A and B. To get it with B and C, you can imagine that it's going to be exactly the same. That sine of B over B would equal sine of C over C, or B over sine B equals C over sine C. So those would both be equivalent over there. So you can now imagine that if we put all of this together, we can form the law of sines. And so the law of sines is all three of them, but you don't need to use all three of them. So we have sine of the angles up top and then their opposite sides below. And so if you notice that where A is in the triangle, little a is across the triangle from it. And the same thing is true for all of them. And then remember, this could also be written in the other way as well. So that's your law of sines. You don't need all three. You can just use two, which is what we'll use in a triangle, but you have flexibility that you can use any of the two that you need because they're all equal. So the law of sines is used to determine the measure of missing angles and sides of triangles. And this is probably the most important part. When we're given the measure of two angles and a side, so we need to have AAS or ASA, or the measure of two sides and a non-included angle. So that's going to be SSA. And so to kind of remind you what those look like, in my triangle, if I have information about two angles and a side, so I have two angles and a side, this is AAS. So we have information about two angles and a non-included side, or I could have information about two angles and an included side, so that would be ASA. And then the one that we don't use to prove triangles being congruent is SSA. So that means that I have two sides and a non-included angle. And so if you have any of these, then we're going to use the law of sines. That would be a perfect opportunity to use the law of sines. However, if we have any of the other ones, we're going to need to use law of cosines, and we're going to talk about that in just a second. So again, these are the pictures of what each of these look like. Okay, so let's talk about law of cosines. So we cannot use the law of sines when we're looking for the measure of missing angles and sides of a triangle when we have two sides and an included angle. So if I have something that looks like SAS, so in my triangle, I have two sides and an included angle, or possibly I have all three sides. These are all opportunities to use law of cosines. So law of sines we use for the top three here. Law of cosines we use for these bottom two. Okay, so to work through this one, we're going to start, you're probably going to be able to hear my dog. I'm sorry about that. So sketch an altitude from vertex C and label it K. So I'm going to take my altitude all the way across again and label it K just like we did before. Now side C, so I'm just going to kind of point out that this whole thing here is C. So I'm just going to cross this out for a second. So we're going to label one side to be X, and so we can kind of work through this with our variable X. So I'm going to say that from this intersection here to B, I'm going to call it X. And if the whole thing is C, then this would have to be C minus X is what's left. So we already sketched the altitude. We've used a variable to help us write an expression for both of these pieces. Now we're going to use the Pythagorean theorem to help us write two equations with these two triangles. So again, I have my pink triangle that we've had before, and then I also have our blue triangle here. So to use Pythagorean theorem for the blue one is quite simple. So we would have x squared plus k squared would equal a squared. And then on the other side over here, we would have c minus x quantity squared, because that's a whole side, plus k squared is equal to b squared. So what we're going to do now is we're going to isolate k squared in both of them. And I also want to expand this binomial here. So again, if you see something squared like that, it's the same thing as c minus x times c minus x plus k squared equals b squared. So this would be c squared minus 2cx plus x squared plus k squared equals b squared. I just FOILed this out to get there and then combined like terms. And so to get k squared by itself, I need to move all of this to the other side. So k squared would equal b squared minus c squared plus 2cx plus x squared. And then we're going to do the same thing on this side, although it's much easier. K squared would equal a squared minus x squared. So if that's true, right, they both equal k squared, then we can set them equal to each other. So I would have a squared minus x squared equals b squared minus c squared plus 2cx plus x squared. So as you can tell here that we have kind of a really ugly looking equation. We just kind of followed through here. We wrote the equations here, and now we want to rewrite the equations without x, and so I want to solve for b squared. So I need to figure out how I can solve this equation for b squared and then start removing and getting rid of x. So let's see what happens. So I'll just rewrite this down here. So a squared minus x squared equals b squared minus c squared plus 2cx plus x squared. So I'm going to isolate b squared, and so to do that I need to move everything to the other side. So I have a squared minus x squared plus c squared minus 2cx minus x squared. Oh wait, I forgot to subtract the x squared. This should be negative because we moved it over to the other side. I was like, this isn't working out. Okay, so we have minus here. Okay, so that is going to be a positive here, and then that's going to equal b squared. So now what you can see, where I was confused, is that the x squareds are going away, and so all we're left with is a squared plus c squared minus 2cx equals b squared. So we're definitely making strides here, that we've removed x squared, but now we're just left with x. And so we want to figure out a way that we can get rid of x. And so I'm going to look back up here at my blue triangle, because this is where I just have x. Over here it's c minus x. And I want to see, can I use a trig function to help isolate what x might be equal to? And so I gave you a hint here to use cosine of b. So here's b right here. So if I want to use cosine of b, that's going to be equal to adjacent over hypotenuse. So that's going to be x over a. And that's where we got from here. If I'm at b, I have adjacent, and then hypotenuse is a. So if I rearrange this for x, I get a times cosine of b is equal to x. Well, that's good news. I can now substitute this for x into my equation. And what I'm going to do is I'm going to move the b squared to the other side and just switch what side they're on, just because this is how we typically write it. So b squared is going to be equal to a squared plus c squared minus 2c times a times cosine of b. And typically how we write that, because what I did here is I just replaced x with this. And so we typically write things in alphabetical order. So we have b squared equals a squared plus c squared minus 2ac times the cosine of b. And that is your law of cosines. So we actually have the law of cosines. We can write it with any of them. And if you notice, this kind of looks like the Pythagorean theorem, and then we're subtracting all this stuff. And you'll notice that a and c are both located here as well. So if I write this with a squared, I would have that equal to b squared plus c squared minus 2bc times the cosine, and notice whatever the letter is here matches what's on the other side, so that would be the cosine of A. I also have b squared equals a squared plus c squared minus 2ac cosine of b. And the last one, c squared equals a squared plus b squared minus 2ab cosine of c. And the lowercase letters, remember, are the side lengths of the triangle, and then the capital letters are the angle. And so I know it can be kind of difficult to tell with C's, but that's what we're kind of getting at here. Okay, so let's do 2 example problems, and then we'll be done. So in this worksheet, you'll see we're going to do number 1 first. We're looking for finding the side of BC. So first we want to look to see what information do we have. Well, I have information about 2 angles and a non-included side. So that's angle, angle, side. That tells me we're going to be using the law of sines. So I like to use the letters that are here. So I'm looking at BC, we're going to call that little a, and across from the 15, that's going to be little c, and then this one will be little b. So it looks like I have information about a and c. So I'm going to use the fact that sine of 15 degrees over, so really we'll just use letters first. So the sine of a over a equals the sine of c over c. So we'll use sine of a, so a is 59 degrees, over little a, which we don't know, is equal to the sine of c, which is 15 degrees, over little c, which is 10. And so now we want to isolate a. Now you could have set this up in the other direction as well, that we had a over sine of 59 equals 10 over sine of 15. That's totally fine. So we're going to cross multiply. So I have 10 sine of 59 is equal to a times the sine of 15, and then I divide. So 10 sine of 59 over the sine of 15 equals a. So this is what I'm going to be looking for to see this. So we don't use our calculator until the very end. And you're going to want to make sure that you're using degree mode, not radians. So using degree mode, and then we plug this into our calculator, and I find that A is going to be 33.1184, and we'll actually write it as BC, because that's what we're looking for. We're finding BC, is 33.118 yards. And that would be your final answer there. Okay, so the last one that we're going to do, I'm not going to do the whole thing, but it's about this one, and so we'll just set it up to find little c, and then I'll let you find, now we'll just solve the triangle. Okay, so we want to figure out what is the side length that we're missing and the 2 angles we're missing. So currently in our triangle, we have a side, an angle, and a side. So that tells me that we're going to be using the law of cosines to start. So this is little c, so this is big C, so this is little c. Across from B is little b, across from A is little a. So since I want to find little c to start, that's what we're going to use. I have angle c, so we're going to use the law of cosines that has c squared. And so you can refer to your notes for what this is. Or over time, you'll just kind of get used to it. It's like an expanded version of the Pythagorean theorem. So we're going to use this to plug in all of our values. So c squared is equal to 13 squared plus 27 squared minus 2 times 13 times 27 times the cosine of 106. So we're going to use our calculator to kind of help us as we go. So we know that 13 squared and plus 27 squared, I can do that in my calculator really easily. That's 898 minus, when I plug in 2 times 13 times 27 times the cosine of 106, I find out that it's actually a negative value. And there we go. Pen just stopped working. So I get a negative value of 193.497, and I'm going to use the whole value. I've just held that into my calculator. So since I have two negatives, we know that those become positive. So c squared is going to equal 1091.5. And so c would equal plus or minus, right? We would take the square root of that. However, we're dealing with side length, so it's always going to be positive. It'll be 33.038 inches. And so instead of writing it as C, we'll write it as AB is equal to that. So now we found our side. That's great. We can use that for the remainder of the problem, and we want to make sure we store that. So if you want to store it into your calculator, make sure that, again, that you're in degree mode still. And once you have it open, if you look on your calculator above the 9, it says VAR. And if you see above that in blue, it says STO with an arrow. So if you have the answer that's previously in your calculator, if you hit Control VAR, it'll say answer arrow, and then you can just type whatever letter, so like C. And it will forever store that value into C until you restore on top of it. So it's a great way to store values in your calculator. So now we're going to look to find an angle. So let's just go ahead and find angle A. So when I do that, I'm going to use now the law of sines, because I have information about two sides and a non-included angle. So I have side, angle. That tells me that I'm going to be using the law of sines. Okay, so we have the sine of A, which we don't know, over 13, because that's over little a, would be equal to the sine of C, because we do have information about that, so I'll just put little letters for right now. The sine of C over little c. So when I do this, I get the sine of A, which I don't know, over 13 is equal to the sine of 106 over 33.038. So I want to isolate A, and the first thing I need to do is to move the 13. So the sine of A is equal to 13 times the sine of 106 over 33.038. Notice I didn't cross multiply because I need A, so if I multiplied by the other side, I just have to divide again. Okay, now I need to find A, and to do that, I need to take the inverse sine of both sides, because I'm trying to get rid of that sign to get what A equals. I don't want what sine of A equals, I want what A equals. So in our calculator, we'll need to make sure that we take the inverse sine of this whole fraction, and then that's when we're going to get a value that A is equal to 22.225 degrees. And now I could do the same process to figure out B. I could do sine of B over little b equals sine of C over little c, or I know that B has to equal 180 minus the sum of A and C, because I know that all three angle measures must add up to 180, and so if I isolate what I'm looking for, then I can figure out what B is. So B would be equal to 180 minus the sum of A, which we found to be 22.225 degrees, plus 106 degrees. And so when I do that math in my calculator, I get 51.775 degrees. So when it says solve the triangle, you're actually going to solve for every missing piece in the triangle. All right, and that's it.